Happy day, students. Let's see standing waves and longitudinal waves now. The previous classes we saw interference. Now let's see the standing waves. And anyhow, we know that standing waves is also an example of interference only. When the two waves interfere in such a way that one is traveling along positive x-axis and other one is coming from the other side or moving towards negative x-axis. When they interfere, they give us standing waves. The similar thing we have already done in waves in string. So exactly same thing, but we know that when we talk about longitudinal waves, we represent the waves in the form of pressure. Okay, standing waves in pressure wave or longitudinal waves. Okay, so again it's an interference only. So if we say that one wave is represented by, let's say, Pm sine omega t minus kx, and the other one you can say a reflected one also, Pm sine of omega t plus kx. Okay, when we are going to add both of them, y equal to y1 plus y2, we know that what comes, y equal to 2 Pm sine kx cos omega t. Exactly same kind of a theory that we have already studied in waves and string will happen over here. Only difference is, in place of displacement amplitude, here we have pressure amplitude. And what is this pressure amplitude? Again, it is beta ak. Okay, this is beta ak. Now, as we said in the case of waves and string, that standing waves form, or standing waves and practically used to form in musical instruments that use a string. So exactly same way we can see that standing waves and longitudinal waves also are produced in musical instrument, and the best example is flute and all those instruments which are played with mouth. Okay, saxophone, flute and all other instruments like that. Okay, in that one you produce standing waves. So we are going to see how these standing waves are produced in those kind of instruments and what those are called in physics. In physics, we call those instruments as examples of organ pipes. Okay, these are called organ pipe. Two types of organ pipe we have. One is open organ pipe and other one is called closed organ pipe. Okay, now open organ pipe means what? Open organ pipe we make like this. Okay, it's a pipe which is open at both ends. Okay, closed organ pipe means it's closed at one end. Okay, open organ pipe, its examples are flute and all other musical instruments. Closed organ pipe, we can take an example of something like in which we will be using a tumbler. In tumbler you will be putting water at different heights, and you can take the fork in hand and you play it. Normally that's called jaltarang. Okay, those instruments can be taken as example of closed organ pipe. Okay, then this is open organ pipe. Now open organ pipe, when we say, here we take it as atmospheric pressure. Remember that. Here is pressure atmospheric, here pressure is atmospheric. Same way here pressure will be atmospheric. Okay, now if I am going to make the longitudinal wave or pressure wave, if you remember how we made it, then we said that in the longitudinal wave it was something like this, and we said that here is pressure P naught and here pressure is P naught plus beta ak. Okay, so P naught pressure actually is where we can consider that the variation in pressure is 0. Here variation in pressure is plus beta ak. Here variation in pressure is minus beta ak. Okay, so what I am trying to tell you is, if this is an organ pipe, then at this point node will form, pressure node. Okay, why? Because pressure node is 0 variation. In displacement we call it as 0 amplitude. Here we are saying 0 variation. So P naught means pressure node. Here also pressure node. Here also pressure node. Whereas here will be pressure NT node. How can we say? Because we know that it is closed at this end. So when it's closed, when the compression happens, the maximum compression will happen at this end only, because at the other side the gas cannot go or air cannot move. So here it will be compressed to the maximum. So we are calling this as pressure NT node. So let us make first of all the standing wave in terms of pressure. I'll show you that. It is similar to what we have done already in waves and string. So I am making it standing wave. Something like this. Okay, now this is the pressure NT node. This point is pressure NT node. And what is its value? 2 times Pm. Same way this also is pressure NT node. This is 2 times Pm. Okay, that magnitude is 2 times Pm. Okay, now this is node. This is node. And this is node. Again, between node, 2 nodes, consecutive nodes, what is the gap? Lambda by 2. Between NT node and node, gap is lambda by 4. So these all are the same things. Okay, no change. What we have done in previous classes, same thing over here. So now let us think, or let us see basically what are the normal frequencies of organ pipe, as we found in the case of string. Normal mode of vibrations in string, same way normal mode of vibration in organ pipe. So first we are going to study open organ pipe. What are the natural frequencies of that? Let's see. And I am going to make it in both the cases, displacement as well as pressure. Okay, it's your wish. You can see in both ways. So first I am showing you in pressure. This is pressure. So what we said, here pressure is P0, here pressure is P0. So here is node, here is node. Okay, so first one I am making with one loop. Okay, this is pressure node, this is pressure node, and here is pressure NT node. What is this? This is single loop. Okay, same way if I make displacement here. Now this is free end, this is also free end if you talk about displacement. So wherever there is a free end, NT node forms at free end. Okay, so here is NT node. Which NT node? Displacement NT node. Here also displacement NT node. So how to do? Here it's more than one loop we have to make. Okay, because we are making single loop. Here NT node, here NT node, and here node. So what is happening between this and this? What is the difference? Wherever there is node of pressure, displacement NT node is there. Wherever there is NT node, displacement node is there. Again, wherever node is there for pressure, NT node is there. Okay, that we have to remember. So it's like this. Okay, like this. Okay, single node, single NT node, node, NT node, node, NT node. Okay, why like this? Because we know that displacement wave and pressure wave, they have pi by 2 phase difference. That's why this kind of a diagram is there. Now again, this is node and this is node. That means this will be lambda by 2. And if the organ pipe's length is L, then we can say L equal to lambda by 2. Check here also. Now this is NT node and this is node. That means lambda by 4. And this is again node and this is NT node. This is lambda by 4. So lambda by 4 plus lambda by 4. That means lambda by 2. Same. Okay. So we can write L equal to lambda by 2. That means lambda equal to 2L. So frequency is V by lambda. So what are we getting? V by 2L. And what this will be called? It will be called fundamental tone. Okay, this is fundamental tone or first harmonic. Fundamental tone or first harmonic. Okay, let's go for the second one. Now in second one we will make 2 loops. Okay, Let's see. So when we are going to make two loops, now you can ask that how we can make two loops. In the case of strings in guitars, we were having the positions at which we can put the fingers and we can make two loops in strings. Here also, if you notice properly, if this is a flute, I can say, in the flute there will be holes in the side. What these holes are doing? The open holes makes air to come inside and make the pressure atmospheric. So wherever the pressure becomes atmospheric, we get node over there. Okay. So in this one also we can control the position of node and antinode. Okay. So now here what we want, this is again open. So here is a node and here is also node. Now what we want is one more node we want somewhere in the middle. Okay. So it will come like this and then we go like this. Two loops. Now this is lambda by 2, this is also lambda by 2. So total is, actual length is L, but in terms of lambda, this is lambda by 2, this is lambda by 2. That means this is lambda also. Okay. And displacement, if you want to make displacement also, but it's not necessary to make displacement also. But I am just showing you that you can also make it. Here is antinode. Okay. Again here is antinode. Again here is antinode. Okay, in between node and node. So like this, again antinode, like this, then again node, like this, and then antinode. Okay, so this is lambda by 4, this is lambda by 2. And again lambda by 4. So what is total? Lambda. Same. So here we can say is lambda equal to L. Okay. So frequency, we know that V by lambda. So we will write it as V by L, but we don't prefer this form. Instead we write 2V by 2L. Okay. So that we can get whole number multiples of V by 2L. Previous one was 1V by 2L. Now we have 2V by 2L. So what this is called? This is called first overtone or second harmonic. Okay, these are fundamental frequencies of organ pipe. Now you must have understood that what are we going to get over here. Okay, next will be 3V by 2L, then will be 4V by 2L, then will be 5V by 2L. Okay, so normal mode of frequencies for open organ pipe are NV by 2L. Okay, what are the frequencies? Frequencies we are going to get for open organ pipe are NV by 2L. And what is this N? N is nth harmonic. It represents the harmonic. And this is also N minus 1th overtone. Okay, if suppose this is third, 3V by 2L, then it will become second overtone. If it is 5, N is 5, then overtone is 4th. This is for open organ pipe. Let's check closed organ pipe. What's happening in closed organ pipe? Let's see. Okay, this is closed organ pipe. Now we know that here again pressure is atmospheric. Pressure atmospheric means pressure node. And this is the closed end. At closed end what happens? Pressure increases. So there will be antinode. So if you make the fundamental one, what will be the fundamental one? Antinode over here, node over here. So it will be something like this. Okay, the gap, this distance is lambda by 4. If we say length of the pipe is L. If you want to make displacement also, that also we can make over here. In displacement's case, this is fixed end. So fixed end means node and free end means antinode. So how will that be? It will be like this. Okay. Again, pressure antinode, displacement node. Lambda by 4 again. So lambda by 4 equal to L. So lambda equal to 4L. Frequency V by lambda. that is V by 4L. One more we will do. Okay, so this is called what? This is called fundamental tone or first harmonic. Fundamental tone or first harmonic. Let's see the second one, the next one. The next one we'll see. So in that one, we know the basic things are same only. Here is atmospheric pressure, so here will be node and here will be antinode. Now what we want? In between I want one more node. Supposing. So one node here and then antinode. Alright, so now what has happened? Now this is lambda by 2 and this is lambda by 4 and this is L. So what is the length? Lambda by 2 plus lambda by 4, it's 3 lambda by 4 equal to L. If you want to make displacement, that also you can make. Same diagram, only thing is node is here. Same diagram, if you reverse, it will come over here. So it's like this, something like this. Same diagram. Okay, so 3 lambda by 4 equal to L. So lambda equal to 4L by 3. Frequency V by lambda. What will come? 3V by 4L. Okay, this 3V by 4L. So this we will call as what? This is first overtone or third harmonic. So just like string fixed at one end, we were getting all odd harmonics in this one. Here also we will be getting odd harmonics. Okay, it will be 3V by 4L, next will be 5V by 4L, then 7V by 4L. Likewise, we will be getting the harmonics for closed organ pipe. Okay, so these are the normal modes of frequencies of organ pipe, exactly similar to what we have studied in strings. Okay, so let's solve few questions based on that, and then we will see further on this one. Okay, now suppose what kind of questions are asked from us. It says third overtone of closed organ pipe. Third overtone of closed organ pipe. Is in resonance with. Resonance they use, or they use sometimes unison. Both are same words. Okay, organ pipe is in resonance with fourth harmonic of an open organ pipe. Okay, so fourth harmonic of an open organ pipe. Find ratio of length of pipe. Find ratio of lengths of pipe. Okay, so resonance basically means what? Both have same frequency. Okay, third overtone frequency of closed organ pipe is equal to fourth harmonic frequency of open organ pipe. Okay, third overtone. Okay, now in a closed organ pipe. Now what is fundamental tone in closed organ pipe? V by 4L. Okay, first overtone 3V by 4L. Second overtone 5V by 4L. And third overtone is 7V by 4L. That means 2n plus 1. Okay, third overtone, when you say 2n plus 1, that means 2 into 3 plus 1, that means 7. Seventh harmonic, that means 7V by 4 length of closed organ pipe. 7V by 4. This is length of closed organ pipe equal to fourth harmonic. So fourth harmonic, because in open organ pipe all harmonics are present. So 4V by 2 into length of open organ pipe. Now this is velocity of sound. Velocity of sound will be same for both. So you can cancel that. Okay, this we can cancel. Now what we have got? LO, you can take over here, by LC equal to 4 into 2, 8, 8 by 7. This is the answer of this question. Okay, this is the answer of this particular question. Let's do another question then. Okay, another question is the water level in a glass tube of 1 meter length, glass tube of 1 meter length can be adjusted to any position, in the tube. Okay, a tuning fork vibrating at 660 Hertz is held over the tube. At what position of water level? Will there be resonance? Speed of sound is given 330 meter per second. Okay, that's the question. Okay, let's see it then. So here is a tube. Okay, and we are keeping water in it. So water is kept. Okay, so where will be the resonance happening? Resonance will happen in the length which contains air. Okay, so effective length, this is 1 meter. Effective length we are keeping is this. We have to find this length. Okay, the frequency of tuning fork given to you is 660 Hertz and speed of sound is 330. Okay, so we know when 660 Hertz is given and this has to be in resonance. So that means this air column also has to produce what frequency? 660 Hertz. So first I am going to do it for this length and I am considering that this is a fundamental tone, the first harmonic. Okay, so V by 4 into this length must be equal to what? 660 Hertz. I know V value, I am going to put it 330 by 4L equal to 660. This is 2. So L is coming 1 by 8 of a meter. This L is 1 by 8 of a meter. That means how much you have filled this tube? 1 minus 1 by 8. That means 7 by 8 meters you have filled the tube. This is for fundamental tone. Then next one. Now next one what we have done? We have taken little more water out. Now it's something like L1. Okay. Now in this case, we are going to search the second frequency. What is second frequency in this case? Second frequency means is first overtone or third harmonic. In this case, you say third harmonic. Okay, fine. 3V by 4L1, third harmonic. Equal to how much frequency? 660 Hertz only. Okay, put the value of velocity 330 by 4L1 equal to 660. This is 2. So L1 is coming as 3 by 8 of a meter. So this is 3 by 8. So how much you filled it? Again 1 minus 3 by 8. What's coming? We have filled it by 5 by 8 of a meter. Same way, next one we will say 5V by 4L1. 7V by 4L1. Like that one, we can find out different heights of the water that we have to keep it inside this vertical tube to get the normal modes of frequency for this particular tube. Okay, so that's all for now.